In the last video, we laid out a strategy for how we could model random rates of returns using the S&P 500 for our retirement portfolio. And we proposed two approaches. One is we could try to fit a normal distribution to our data, which would fit okay, or we could use what you might call a bootstrapped approach, where you draw samples from the rates of return in the actual data. So in this video, we're going to look at how we actually implement that with a computer. And to start off, you might want to download the data with the rates of return for the S&P 500. So I found Yahoo Finance to be one of the easier websites to use to do this. And so if you give it a range of dates and you choose the frequency and click on historical prices, you can actually get a nice spreadsheet that you can download. And if you do that, you'll get something like the spreadsheet I'll show you in just a moment. Okay. So I've downloaded this data, and now I've got columns for dates, the opening, high, low, and closing prices for the S&P 500. And if we want to get rates of return, we can easily calculate those. So the rate of return, we don't have a rate of return for the first day, but for the next day, we can just create a nice little formula here. We'll take the current closing price, which was E3, minus the last closing price. So that's the change. And then we just want to see what percentage of the original value was that, and so we'll divide that by the original. All right, and so we got, it looks like about 0.01 for a rate of return, or about a 1% return in that particular month. And if we just double click on this little box here, it'll propagate that formula down, and we can even check to see the average of that column, and the standard deviation. And you'll see that I used a different window of time here than in my previous example. So in the slides, we had a mean of 0.054 and a standard deviation of 0.0349. That's changed a little bit because, again, we have a different data set, but they're in the same ballpark. So the monthly returns and the returns for the excuse me, for the standard deviation of those returns are somewhat consistent. All right, so how do we simulate that? Well, let me remember those two values. I will go into Octave here, and I created this simple model to use a difference equation. So what we're going to do is we're going to repeat the same experiment multiple times, and in that experiment we are going to simulate 540 months where we make the same payment, and right now the payment is set to $1,310 per month, and I'm going to store all of the results, all of the balances at every month throughout all of my experiments in a single matrix. And so I did that by creating a matrix of zeros, where the number of rows is the number of experiments, and the number of columns is the number of months plus 1, because I want to actually keep the initial condition as well. All right, so we'll repeat the experiments, and for each experiment we'll do the following. We'll define the initial value to be 0, so we didn't have any savings when we graduated from college. Then for the number of months, we will take the mean, which we had 0.00, let's see, what was it? 0.00712. All right, so that's the average return, and then we're going to add the standard deviation, which is 0.0414, I believe. 0.041058. All right, so that's the standard deviation. And we'll multiply that by a random number that is normally distributed. Multiplying by the standard deviation stretches the distribution to set the standard deviation correctly, and then adding the mean shifts it. So again, the center will line up with the appropriate value. And then all we need to do is incorporate this rate of return into our model, which is exactly like our deterministic model. We'll take 1 plus the rate of return times the value plus our savings. So we're putting away $B each month, and store that as the new balance. And once we've done that for a given set of 540 months, we can save that entire vector in our matrix and then repeat for as many experiments as we want. And if we do that, we can get a plot that looks something like the one that you'll see in the notes. So it takes a moment. Oops, there's a little typo there. Let's fix that. How about we spell figure correctly? And there we go. All right, so each of these individual curves represents one possible future with different random rates of return. And we see that we have a very wide range of different outcomes here. we're basing this on the returns for the S&P 500 for the last 70 years. And so there were some good years and some bad years. And if we happen to draw a lot of samples, we have a lot of good years, then we could have as much as that looks like around $40 million in the best case scenario. But if you zoom in down below, you'll see that there's also some possibility that things will go quite poorly, and you could have, let's see, this is less than $1 million you could have, and that happens sometimes as well. So depending on how the stock market performs during the time that you're saving, and particularly in the early stages, you may do very, very well or not so well at all. Okay, so I'll put this over here. Let's go back to our model. And so this is a model where we fit a normal distribution to the rates of returns, right? We use the mean and the standard deviation, but as we argued before, maybe that's not really the best approach. What you may notice is that that kind of underestimates the risk or the probability of having really, really high or really, really, really low returns. So let me create a new model, which I'm going to call the bootstrapped model. And instead of using these random rates of return, what I would like to do is I would draw random rates of return, not from a normal distribution, but rather from the data itself. Okay? And so I will do that as follows. First off, I am going to create R. Well, let me look at the data first of all. We have in our column here, we have starting in column 3, we have a total of, it looks like 841 rows. So if you subtract the first two empty rows, that means we have 839 different rates of return. All right, and I am going to highlight that, and we're going to copy that. Now there are multiple ways to get this data into Octave. Don't copy it, or don't actually type it by hand. That would be incredibly tedious. We can actually copy and paste it. We just have to get a little clever. There's also ways of importing spreadsheets, which you can read about on your own. But for our purposes, we don't really need that. So what I'm going to do is I'm going to make R be a matrix of zeros. So zeros, it's going to have 839 rows and 1 column, which is exactly the dimensions of the data we want to copy. All right, and now if you just double click on the variable R in this workspace browser, it'll bring up a spreadsheet-like environment. And if I just paste, I'm pressing Control V on my keyboard, you'll see that all those rates in the return are now there. And so we can just save that. In fact, we could even save the data to a file if we wanted. Return data. All right, and now that we've got that, let's go into our code. Instead of drawing a random normal value, what we'll do is we'll set our rates of return. Let me actually rename that variable. Returns equals R. All right, so now returns has all the information. And so what I'll do is I'll pick a random number. So I is going to be a random integer from 1 to the length of the returns vector. So I'm going to pick a random location in that vector. And then my actual rate of return will be the value located in that spot. And so this is going to allow me to actually have returns that are consistent with what we've seen in the past, rather than relying on this normal distribution model. And what you'll see is it doesn't change things too much, but it will give you probably a slightly wider range of outcomes, because we had some really good and some really bad outcomes that are not likely to occur with a normal model. All right, so do we make any typos here? Returns, what do we call it? Oh, I cleared the variables. So let's try that again. Thankfully, I saved that data. What did I save it as? Return data. All right, so now R is back, and we called it returns equals R. And instead of doing clear all, I don't want to delete the variables. We'll comment that out. And now when we run it, hopefully things will work out a little better. All right, it's thinking. All right, and there we go. So very similar distribution of outcomes, ranging from somewhere around $40 million all the way down to, let's look at the lower end. We have some outcomes where we only had around 1 million. Okay? All right, so those are 2 ways of sampling from that. And once you've got all of this data, you can start to ask questions about the data and compute probabilities. So here, I did a total of 100 experiments. And suppose we want to know, well, how often did I actually meet my goal? What we can do is we can look at the final values of our experiments, which is the last column in the matrix called AMAT that I created. All right, so those are final values. All right, and that is going to be, all right, so those are the actual amounts that I had in my account at the end of the time. And I can then say, well, maybe we should look at the histogram of that. Okay, and you see that the most common outcome is that we have, looks like, less than $5 million, but there's also some chance we end up doing a whole lot better than that. All right, so here the histogram, each bar represents the frequency of each range of final values. And so we've got one that corresponds to less than 5 million, one that looks like maybe 5 million to about 7 or 8 million, then one up to about 10 or 11 million, and so on. And so the heights of those bars tell us about likelihoods. If we divide the height by the total number of experiments, we can actually get probabilities. So another way we can do this is our goal was 2.5 million, right? So we can actually use conditional statements to actually count things up for us. So for example, if you type final values greater than 2500000, so that's 2.5 million, notice it gives you a matrix of ones and zeros, where the ones represent the true values and the zeros are the false values. So if we actually met our goal, we'll have a 1 here, and a 0 would correspond to failing our goal. And so if we add that up, which there's a command called sum for doing that, you'll see that 90 times out of 100, we actually met our goal in this scenario. Okay, so 90 times out of 100 means there's a 90% chance that we will have 2.5 million if we save according to this strategy. And if we change our savings, then we could also change this probability. So maybe we decide, wow, that's a lot of money to save each month. I don't know if I can afford that. What if I save a little bit less? Can I still hope to reach my goal? Well, we can certainly check that. All right, so let me copy these commands here. So the probability of success would be, we said we'll take the sum of the final values, and we're going to add up the ones that correspond to meeting our goal. All right, is that 250 million? One too many zeros. All right, and we'll divide by the number of experiments. Okay, so that's our probability of success. And I'll change my payment amount. Let's suppose that we decide we can only afford $1,000 per month. All right, so we're going to save a little bit less. We can run our simulation. And it's thinking. All right, so we're doing 100 experiments. And there we go. So there's the outcomes. Wow, we had one that we did really, really well here, even though we were saving a little bit less per month. So sometimes you get really, really lucky. But again, there is some chance that we didn't do quite as well. And if you look at the number of curves there, you'll see that the number that are below 1 million seems to be higher here because we were saving less each month. So here it says that we have a 75% chance of meeting our goal. 75 out of the 100 experiments actually had more than 2.5 million, whereas the other 25 did not. All right. And so I hope that what you appreciate here is the power of a Monte Carlo simulation. We can calculate pretty much any probabilistic question that we'd like to ask about this process now that we've got a stochastic model in place. And that will include things like, well, we'll go back to our slides here. Determining probabilities of success under different scenarios. So for example, here's a histogram with slightly different parameters than the ones I showed you, where we did 200 experiments, and you can see that if you save only $500 a month, you have some chance of getting your goal, but it's not likely. If you save $1,000 a month, Again, this was different rates of return. In this experiment, I got about 53% of the time you achieved the goal, and then about 70% with the amount that we discussed from the deterministic model. And if you're even more aggressive in savings, then you can be almost certain that you'll reach your goal. Okay, and so this is the probability after 67 years, but there's no reason why we couldn't adapt this if we want to talk about retiring early or retiring later. If you want to change your types of investments, you could adjust the way that you draw random interest rates. There are a whole lot of different wrinkles that you could throw into this model, but all of them are based around the fundamental principle that we can use a difference equation to describe change over time, and we can use randomness, which is based on changes in real-world data, to try to account for the variety of different outcomes that we could observe. And if we can build a model to describe a scenario, then we can count up the number of different times the model predicts each outcome and use that to estimate probabilities.